Can bases burn you really badly? They can, yeah. They actually both do. If you've ever used something like a solution called lye, which is used sometimes to clean metal parts and that kind of stuff, that's a strong basic solution, strongly basic solution. Most strong cleaners are strong bases, so things like oven cleaner, and those can burn you too, right? All right, so we've got some burning on both sides of the spectrum. Any other ideas? Other definitions? What makes an acid or a base?
Sour.
Sour, yeah. So acids are sour. So should we just taste everything and see if it's an acid or not? But you're right. Acids are sour. Acids are what causes candy to be sour and gum and delicious things like that.
Does it have to do with like pH levels?
Has to do with pH levels. What do you know about pH levels?
The more acidic, the less the number.
Okay, the more acidic, the less the number. What is the pH? You know, what is it a measure of?
Acidity.
Yes. How do we measure that? We'll get into all this. I'm just kind of trying to see how much.
It's something 7.
Yeah, you can measure with the papers, but what are those papers seeing? What are they doing? The pH. So we're back to that. Acids are acids and bases are bases. pH paper measures pH, so it's pH. So pH. Well, we're going to talk about that because that word strong has a few different meanings and can be talking about some different things. But asking these questions, what's acids and bases. By the way, if acids are sour, what do bases taste like? Yeah. Well, first of all, don't eat it. But like there are food-safe bases. One would be baking soda. Anybody ever eaten some baking soda? What does it taste like? Not good. Yeah, it's kind of bitter. Sometimes a little soapy tasting. Bases can taste bitter and soapy. Bases aren't usually used as much in cooking because they don't taste as good by themselves. But some ways that they are used, of course, in things like baking soda, to help rise things and to give that kind of nice bitterness in biscuits and those kinds of foods. But also even lye, that really strong cleaning solution, which we call sodium hydroxide, which is chemically sodium hydroxide, is used in cooking. If you ever had a pretzel, like a soft pretzel, the difference between a pretzel and regular bread is that the pretzels are boiled in a basic solution, and that's what gives it that really brown color. The reactions that cause proteins to brown, known as Maillard reactions, are promoted by more basic environment. So if you use things like lye, then you'll get that really nice browning. One trick that some people use when cooking is if you put some baking soda, if you kind of rub baking soda on meat, for instance, and let it sit for a while before you cook it, it will brown at a lower temperature. So you can get nice, crispy, brown meat skins and stuff like that without needing to use the fryer. So that's kind of a trick that we use sometimes. All right, so we've got these ideas of acids and bases, and the answer really is that the definitions are complicated, meaning that there are multiple definitions. There are different ways that people have described acids and bases based on their chemical reactivity. We're going to stick to one particular definition, and then we're going to look at what that means and how that looks in a chemical reaction. This particular definition is known as Bronsted-Lowry for the people who developed it. So this definition is based on chemical behavior. Acids donate H+, and bases accept H+. Let's talk about what that means. What's H+? Hydrogen ion. So it's hydrogen that's missing an electron. What else is hydrogen atom made of besides an electron? a proton. So hydrogen atom is just one proton in the nucleus, no neutrons, and then one electron. So if you take that electron away and you make a hydrogen ion, what do you really only have left? Just a proton, yeah. So a hydrogen ion is really just a proton. So we might use those terms interchangeably. Donate, accept hydrogen ions, donate, accept protons. Doesn't mean the same thing. Yep.
So in high school, my chemistry teacher said if you eat a lot of junk food, your body's pH becomes acidic. Is it due to saturated fats giving off their hydrogen?
No, it isn't true, actually. Your body, and we'll talk about this later. Sorry to your teacher, but your body adjusts its own pH. It has something called a buffering capacity. We'll talk about buffers, but those are ways that it controls the pH. And actually, if your body got even a little bit out of the pH range that it should be, you would have like really serious problems. And there's names for that, acidosis and alkalosis. They're not caused by your diet. They are caused by things like hyperventilating, getting too much CO2 or not enough CO2 in your blood. So we'll talk about what that is, but it actually has nothing to do with what you eat. Yeah.
But on average, everybody has the same pH lower.
Right. Yep. Right around the same pH. And we'll talk about body pH and how that affects things. So yeah, I'm not sure. I think there's a lot of that out there. You'll see a lot of food saying like pH balanced or helps, pH something or other. But your body actually balances its own pH and does a fine job of it. The only exception to that is if you eat things that are really acidic, it's bad for your teeth because your mouth gets to be an acidic environment and that breaks down your enamel on your teeth. And then if you have things like heartburn or ulcers or other types of gastrointestinal things, sometimes acidic foods can exacerbate that. But by the time it gets into your bloodstream and actually into your system, there's no real, your body takes care of that and balances the pH for you. All right, so let's talk about what this means in a reaction standpoint, and then we'll look a little bit about how we talk about these things. One kind of basic, or I shouldn't say basic because that's basic, but like simple, beginning sort of important acid-base reaction is just a reaction of an acid with water. Anybody remember we a couple weeks ago did those tests where we made some various solutions and then we showed whether or not they were conductive, whether or not they were electrolytes with the light bulb. And we used HCl as one of them, which is hydrochloric acid. Anybody remember, did the hydrochloric acid, was that conductive or not? Nobody remembers? Okay, it was. It was conductive. It was strongly conductive. Even a weak solution of HCl is conductive. So what does that tell you about what's in the solution? Yeah, somebody said it. What did you say? Ions, yeah. So that means there's ions in the solution. There's positively and negatively charged particles in that solution. So if we have an HCl molecule and we put it in water, that means that that's going to break apart into ions, H plus ions and Cl minus ions. So we can draw that. Say in water. We've got our HCl molecule, and that breaks up and becomes H plus and Cl minus. So that's the ions that we see in water that are causing the conductivity. Those are the electrolytes, H plus and Cl minus. Now, that's not exactly right because these ions, unlike something like sodium ion, a hydrogen ion actually doesn't stay by itself. It reacts with water. So in a solution of HCl in water, we don't actually have free H plus ions floating around. Instead, we have something like this. So we'll say, actually, we can show the water reacting, or the HCl reacting with an individual water molecule and forming this. So rather than the H just simply splitting off from the Cl and becoming H+, the H reacts with the water and sticks onto the water to make this new ion H3O+. Does anybody know what that's called? This is called a hydronium ion. Hydronium ion is simply water with an extra proton on it, with an extra hydrogen ion attached to it. And that's really what we see in a water solution of an acid. So when we say that acids donate H+ and bases accept H+, in this example, the HCl is acting as an acid and the H2O is acting as a base because the H+ is being transferred from the HCl to the H2O. You see how that works? So the H is going off of that one and going to the other one. A big part of what we're going to be doing in this chapter is tracking that behavior. Where is that H going? Where is it coming from? And where is it ending up on the other side? So in this case, we've got it like that. Now, the other thing that we need to know about acid-base reactions is they're not just one way. They do something called equilibrium, which means they're always going backwards and forwards. And depending on which reagents you're talking about, some are going to go more backwards and some are going to go more forwards. In this example, the forwards direction, left to right, is favored because we know we form a lot of ions in solution. If the backwards direction were favored, then we would not have a strongly electrolytic solution. So that's the basic definition of how acids and bases work. Now let's take a little aside here and talk about how we name acids specifically. Bases don't really have a special naming. We just name them like ions because they're usually ions, but acids have some special names. So let's talk about that, and then we'll get back to some of these reactions. When we name acids, we name them from the ions that they come from. So there's two types of names that we're going to deal with. One are what we call the binary acids, which are just two things, just H and one other thing. We'll say HX. So H and then something. Those are pretty easy. We've seen some of them. So chloride ion with an H gives us HCl. And what do we call that? Yeah, that's hydrochloric acid. So then chloride ion gives us HF. What do you think that one's called? Yeah, this one would be hydrofluoric acid. Good. You kind of see how this works? A bromide ion could give us HBr, which we might call, yeah, hydrobromic acid. Not so tough, huh? Not yet. Okay, so that's how we name those binary acids. If you just have H and then one other thing, it's just hydro and whateveric acid. Pretty straightforward. Okay. The other category is what we call the oxo acids, which are acids with oxygen in them. So it's usually going to be H something, something, O, something. That kind of a form. And X could be whatever. Doesn't have to be the same thing. Same idea. We take the ion that these things came from, and then we name the acid based on that, but we leave off that hydro part. So let me give you an example. What is the name of this ion? Nitrate. That means that the acid formed from nitrate, hydrogen has a 1+ charge, nitrate has a 1- charge. So if we want hydrogen and nitrate together, we've got to have one of each. So that makes HNO3, and we call that nitric acid. So same idea as before, but we leave off the hydro for these types of acids. But you do need to know what the ions are called, and a couple of them are a little bit weird. So let's go through a couple of the ones that we might know about. What's this ion called? Yeah, this is sulfate. And so what is the formula of its acid going to be? Yeah, this time we've got a 2- ion, so we need 2 hydrogens to balance out that charge. So that's H2SO4. And we call that sulfuric acid. So it's not quite as easy in that it seems like it should be, if it's nitric acid, it should be sulfic acid, but it's actually sulfuric acid. And then another one that doesn't quite work nicely like that. What's that ion called? That one was on the exam, I think. Phosphate. And phosphate's going to get 3 hydrogens because of its 3- charge. And the name of this one is phosphoric acid. Phosphoric acid is actually important in food also. It's in soda. Helps it give it its particular flavor. That's also why pop, like Coke and Pepsi, can do all kinds of crazy stuff like clean hubcaps because of the high phosphoric acid content. You can actually clean metal pretty well with soda. That's how you know it's delicious. You can clean metal with it. It's got to be good for you. All right, so that's basically how we name the acids. You're not really going to encounter many more weird ones than this, but that's the basic idea. All right, so let's go back to some reactions and look at how we can think about acids versus bases. So remember that definition of acid and base is not specifically about a molecule. In other words, HCl, we call it hydrochloric acid, but there could be a situation where you have a reaction where the HCl molecule acts as a base and actually accepts a hydrogen. That's exceedingly rare, which is why we usually call it an acid. But for other molecules, it isn't, like water, for instance. Let's put back this reaction that we looked at before, HCl plus H2O, and the products are hydronium and chloride in this particular reaction. One of the things I want you to be able to do here is for any given reaction, indicate which molecules are acting as bases and which molecules are acting as acids. So in this case, if we look going from left to right, which molecule is acting as an acid? Which molecule is giving up its hydrogen? HCl. HCl is losing its hydrogen to become Cl-. So we would call this one the acid. And of course, that's hydrochloric acid, so it makes sense. That means that whichever molecule accepts that hydrogen is called the base. And in this case, that's water. We can do the exact same thing on the other side. So now imagine that we are starting with the reagents on the right, and we're going from right to left. So which of those two is losing its hydrogen as we move right to left? Yeah, it's got to be the H3O because the other one doesn't even have any hydrogens to lose. Does everybody see that? So this one loses its hydrogens, and that means that this one is the acid on the other side, and this one is the base. molecules in a reaction on one side or the other that differ only by that one hydrogen that they lost, or sometimes multiple hydrogens that they lost, are known as conjugate. So the HCl and the Cl differ only by that one H that transfers. You see that? Otherwise, you get the same thing. So those are known as a conjugate acid-base pair. And then similarly, the H2O and the H3O plus, the water and the hydronium, are a conjugate pair because they also only differ by one hydrogen. We could say then that hydronium, let's write this down actually, hydronium H3O plus is the conjugate acid of water, meaning that it is water plus a hydrogen ion. What is that we could also say in the other way then, sorry, we'll do that in a minute, that HCl, HCl is the conjugate acid of Cl minus, because it's Cl minus plus H plus. And then we can go the other way and talk about the conjugate base. So we would say chloride, Cl minus, is the conjugate base of HCl. It's HCl, take away an H plus, and you've got its conjugate base. And then water is the conjugate base of hydronium. You take hydronium, you take away a hydrogen, and you've got water. So we can't use this particular reaction to answer this question, but see if you can answer what is the conjugate base of water? What is the conjugate base of water?
Hydroxide ion.
Hydroxide ion. You see that? How do you know that?
Without the one from.
Right. So you take away a proton, you get a conjugate base. So to take any molecule, take away a H plus, and you've got its conjugate base. Take any molecule and add H plus, and you've got its conjugate acid. The thing that's tricky about this, most people get the idea of adding or subtracting H. The thing that can be tricky is you have to watch that positive charge, because we're taking away H plus, we're taking away an ion, not a neutral atom. So when water loses H plus, water is a neutral molecule, it has no charge. But when it loses H plus, it becomes OH minus, because it's not only lost a hydrogen, it's also lost a positive charge. If you take away a positive charge, you're left with a negative charge. Similarly, if you take water, a neutral molecule, and you add H plus, you're not just adding hydrogen, you're adding hydrogen ions. You have to add a positive charge to what you get also. So the conjugate acid of H2O is not H3O, it's H3O plus. It's an ion because you've added that positive charge as well. We can see water act, so in this particular example, water acts as a base and takes a hydrogen from HCl. We can also see water act as an acid For instance, when it reacts with ammonia. Ammonia is NH3, and that is a base. We don't have as nice ways of looking at as categorizing bases as with acids. So it's just certain molecules act as bases and others don't. But ammonia can react with water and form ammonium and hydroxide. Once again, we want to look where the hydrogen is going. It's going from the ammonia to the water. Or, I'm sorry, it's going from the water to the ammonia. Ammonia is becoming NH4 plus. Water is losing that H plus and becoming OH minus. You see that? So that means that we can talk about going from left to right. This is acting as a base, and this is acting as an acid. And then going from right to left, which one's acting as the acid? Yeah, NH4 plus is acting as the acid, and hydroxide is acting as the base. Notice how not only the number of H's change, the number of hydrogen change, but the charge changes as well. We've got two neutral molecules on the left, we've got two charged molecules on the right. So when the hydrogen transfers from water to ammonia, it also takes its positive charge with it. So whatever it sticks to ends up having one more of a positive charge. Okay, let's practice this a little bit. Find my examples here. I'm going to write down a bunch of molecules or ions, and I want you to try to come up with a conjugate acid and a conjugate base for each one. All right, so we've got four molecules or ions here. NH2 minus, H2O, CH3OH, and OH minus. In each case, I want you to try to find a conjugate acid. So that's going to be the acid formed when this thing acts as a base. So that means that we're adding H plus to find the conjugate acid. And the conjugate base is when we lose H plus. I want you to try to write something in for each of those blanks, and then we'll go through it and see how you did. All right, got some bases, acids and bases here. Let's look at the conjugate acids first. If you add H plus to NH2, what do you get? NH2 minus, what do you get? NH3, right. And it's just neutral, right? Because you started minus. If you add a plus, then you come to neutral. Okay. So then what's the conjugate base of NH2 minus? NH, and what's the charge? It's going to be 2 minus. Because it started as minus, we took another plus away, it's going to go to 2 minus. Okay. H2O, we just did that one, so the conjugate acid is hydronium, and the conjugate base is hydroxide. CH3OH, that's methanol. The conjugate acid is going to add a hydrogen. Where we put it, because there's kind of two spots there, we'll talk about why that is when we get in the organic chapter. For now, it doesn't really matter. So if you put CH4OH or CH3OH2 is fine. And then that's going to be now have a positive charge because it was neutral. So when it gets the H plus, it now has a positive charge. And then the conjugate base, we're going to take off that hydrogen and make sure that the charge changes as well. So it's CH3O with an overall -1 charge. That's the number one thing I see people get wrong on looking at these conjugate acids and bases. They understand about moving the hydrogen one way or the other, but forget about the charge. So you have to change the charge accordingly because a hydrogen ion is positively charged. All right, and then hydroxide, what's the conjugate acid? Yeah, water. Right, you add an H plus, you've got H2O neutral, and then what's the conjugate base? Yeah, it's going to be oxide ion, O2 minus. Because it started out OH minus. If we lose an H plus, then we're left with an O with 2 minus. Yeah.
For the CH3OH
Yeah.
on the base, do we like the only way to write it like CH3O minus, or we can write CH2OH?
That's okay. Well, this is better, but I don't expect you to know why. We'll get into that in the chapter. I would accept either one at this point. When we get into organic chemistry, you'll see why that is. The organic molecules, made of carbon, hydrogen, and oxygen, we tend to spell them as the way that they're connected, rather than just putting all the atoms together. So in this case, it is actually the hydrogen that's connected to the oxygen that gets taken off. And that's why we do it that way. But if you did CH2OH, that would be okay for our purposes as well. All right, so you think we can do that? Find conjugate acids and bases, given reaction? All right. Let's talk about another type of acid-base reaction. Which is a neutralization reaction. A neutralization reaction is usually some sort of aqueous acid, so acid that's already been dissolved in water, plus an aqueous base. So a base that's dissolved in water. Now acids, we talked about how to identify acids with the hydrogen out front. Usually has the hydrogen out front. With bases, it's not always so simple, but most of the bases we're going to be looking at are hydroxides. So hydroxide salts tend to be bases. And so a neutralization reaction might look something like this. Aqueous hydrochloric acid plus aqueous sodium hydroxide gives water, which is a liquid, and sodium chloride. The reason it's called a neutralization reaction is because we've taken something that's very acidic, HCl, We've taken something that's very basic, NaOH, we've put them together and made something neutral. Water is neutral. We'll talk about the pH scale and how we know what's acidic or basic probably next week. But that formation of water is an important part of a neutralization reaction. So a neutralization reaction will generally form water. Now, really, if you analyze this, the type of reaction that this is, it's really a double replacement. The H over here goes with the OH, and the Cl goes with the Na. So H with OH is H2O, that's water. So it's really a double replacement reaction, but because it forms water, it kind of has a special name, and we call it a neutralization reaction.
So a neutralization reaction always forms water? Is that what makes it?
Yes. Well, a neutralization reaction always becomes neutral, usually forms water. I don't think we'll see any examples where it doesn't form water, but it is, I suppose, possible. All right, so the next thing we're going to look at today is strength. Maybe I could spell it correctly. Let's see. The thing that determines acid-base strength is this reaction that we saw before, this dissolving in water. And that's an important distinction because it's not how we think about strength in terms of acid or base strength. So remember this reaction from before. And we said that it goes both ways and that we form hydronium ion and chloride ion. This could kind of be a general definition for any kind of acid. It reacts with water, forms hydronium ion, and then whatever else is left, the conjugate base of the acid. The degree to which that hydronium ion is formed tells us about the strength of the acid. So a strong acid means that in this reaction, we're not kind of evenly going back and forth. For a strong acid, and HCl is a strong acid, we go almost entirely in that direction and maybe a tiny bit backwards. But we're forming lots and lots and lots of hydronium. We're completely dissociating. Same thing with sodium hydroxide in water. We can't really draw that in the same way of reacting because it's not really reacting. But sodium hydroxide in water is going to form lots of sodium ions and lots of hydroxide ions. And that makes that a strong base. So strong, in our definition of acids and bases, refers to a strong electrolyte. So when we say a strong acid or a strong base, we're talking about something that forms lots and lots of ions in solution. It does not have anything to do with its corrosiveness or those kinds of properties. So to say an acid is strong does not mean that it will burn you more than a weak acid. It has to do with the way that it dissolves in solution. This can be a problem when we get into this. If we get into this confusion, I'll give you an example. HF, hydrofluoric acid, is a weak acid. When it reacts with water, it mostly just stays the same and forms just a little bit of ions, a little bit of hydronium and fluoride. But mostly when you dissolve HF in water, it stays HF. And so this tells you that the acid is weak because it doesn't form a lot of ions in solution. If we got a beaker full of, well, not a beaker full because it dissolves glass, but a plastic beaker full of HF, we would not see the light bulb turn on very bright. It would just be really dim because it's not forming a lot of ions. So we call that a weak acid. Now that said, HF is one of the most dangerous acids you can possibly have. It dissolves glass, so you can't keep it in any glass containers. It dissolves stone and brick and anything made out of rocks, so you can't keep it in any of that kind of stuff. You can only keep it in plastic or stainless steel because it doesn't react with the organic molecules in plastic and it won't react with the stainless steel. But this is kind of what I call like cartoon acid. You know, like on cartoons, somebody spills acid on the floor, it goes through like 3 floors and just kind of keeps burning everything away. Most acids don't do that, but HF actually does because it can eat through all that stuff. This is the kind of acid you'd want if you want to like dissolve a body or something like that. It'll leak through bone, all that kind of stuff. So, you know, definitely dangerous stuff. I don't even think we have any in the chemistry department here because if you don't need to use it, it's not the kind of thing you want to just have around for fun. So, but by these definitions, we consider that a weak acid. So it's important that we keep that straight and that we understand that strength has to do with how strongly it dissociates in water. That means how strongly it forms ions in water, not how dangerous it is or how much damage it can do. So I think keep that straight, maybe?
I haven't known these examples, which one is?
You don't. So you don't know what is going to happen when you just look at a structure of an acid. You wouldn't know that HCl is strong, HF is weak. So here's how we tell. The easiest way to tell is to know this list. There are only a handful of strong acids. These are acids that completely break apart in water. Most acids are not strong. Most acids fall in that weak category, where they only dissociate a little bit. But there's a handful of strong ones, and they're the ones that you've probably heard of anyway. So things like HCl, hydrochloric acid, nitric acid, sulfuric acid, hydrobromic acid, hydroiodic acid, you may not know about those as much, and perchloric acid. You don't need to know all those, by the way, but that's the whole list. So all the other acids fall in that weak category where they won't form lots of ions. So hydrofluoric acid, carbonic acid, phosphoric acid, acetic acid, anything else that we would have would not be in this category. That's the way you can tell them. If it doesn't fall in this category, it's not a strong acid. Now, how we can measure that is through something called pH. Since strength is based on how well something dissociates in water, how well it forms hydronium ion in water, to measure the strength of an acid, we measure how much hydronium ion is formed. And that's what pH is. So when you put that little pH paper, when you touch some water to the pH paper and it turns color, it's turning that color based on how much hydronium ion there is in that solution. There are also pH meters, which is a electronic instrument. You can stick a little probe in your solution and it will read you the pH. And that is also a measure of how much hydrogen ion is in that solution. So how do we come up with pH? Well, it has to do with concentration. Let's look at pure water. Now we know pure water is basically a non-electrolyte, but it does actually form a little bit of ions. It actually reacts with itself to form hydronium ion and hydroxide ion. So pure water will actually act a little bit like an acid and a base and transfer hydrogen like that. But since we know from like the light bulb experiment, it certainly doesn't form a lot of ions, right? Not really much of an electrolyte. And in fact, if you measure this, the concentration, which a shorthand that we use for concentration is brackets. If you put brackets around a chemical like that, that means you're talking about its concentration. That concentration is 10 to the minus 7th molar. That's a really small number. That's right. Yeah. All right, everything's okay out there. Okay, so 0.00000001 molar. That's small concentration, but that's the concentration of hydronium in water. So anything more than that, we would say is acidic. Anything less than that, we would say is basic. In other words, if there's a greater concentration of hydronium relative to hydroxide, we call that an acid, and if there's less, we call that basic. Now, the way we talk about this, these are kind of messy numbers to deal with. We don't like 10 to the minus 7. We don't like dealing with that. So we come up with this thing called pH. The pH is the negative log of the hydronium concentration. I don't know, sounds celebratory. If we hear gunshots, we'll lock the door. So anyway, the pH is the negative log of the hydronium ion concentration. Anybody know about logs? Do that in your math classes? What do logs tell us?
Isn't there a log button on your computer?
There is a log button on the calculator. What does that do? What's it for? You know what it does? A log tells you an exponent. So a log of something is saying 10 to what power is the log. So the log of 10 to the minus 7 is minus 7. If you don't believe me, you can check your calculator, the button on your calculator. But the log of 10 to the minus 7 is just minus 7. So the negative log of 10 to the minus 7 is just 7, because you flip the sign. Negative of a negative is a positive. And that's where this pH scale comes from, and that's why 7 is the middle of the pH scale. So we take the hydronium ion concentration, we take the negative log, and that gives us the pH. The thing that gets tricky about this is it ends up kind of flipping it. So if you had a hydronium ion concentration of, let's say, 10 to the minus 5 molar, 10 to the minus 5 is a bigger number than 10 to the minus 7. It's 100 times bigger. But then the pH is what? pH is 5, right? The negative log. And that's smaller than 7. So that's where we kind of get turned around a little bit. A greater hydronium ion concentration leads to a lower pH, because it means it's going to have a smaller negative exponent. So that means that our pH scale is going to go from very low, we'll say about 0, although you can have negative pH too, to about 14. So here's pure water, is purely neutral right in the middle. And then between 0 and 7, we're going to call those acids or acidic. And then between 7 and 14, we're going to call that basic. And that's a physical measurement that you do. So we can't say that like HCl always has the same pH. It always has something called a pKa. We're not going to get into that. But it doesn't always have the pH because it depends on how much you put in the water. A very low concentration is going to have a higher pH. A very high concentration is going to have a lower pH of HCl. So it's important that we understand the scale in terms of what things are more acidic and what things are more basic and how we, determine that. In a couple of weeks, we'll do a lab. We're a little behind on our labs because next week we're doing another solutions lab and then we'll do the acids lab the week after that. But then we'll actually get to see this stuff kind of in action. And we'll get to test some pHs and play with some indicators and things like that. So it'll be good. All right, we'll stop there. Have a great Halloween. Be safe. Eat lots of candy. And whatever. And Tuesday we will blow up a pumpkin. Because I want to do it today, but we have to do it up in lab. Yes.
Yes.